final chapter, Chapter 7. We're starting to look at what we can do with these integrals that we've learned how to do at this point. And so the first thing we're going to start with, instead of finding the area under a curve, we're going to start worrying about the area between two functions. And that's going to be a little bit more complex, although not something that we can't figure out. So area between curves. What we've done in the past, instead of having two curves, we'd have one, for example, like this f of x right here. And we would probably instead be trying to find the area underneath that curve in between this a and this b. So if I wanted to find that area underneath that f of x function between a and b, we'd just integrate it. We'd integrate from a to b of that f of x dx. And that would give us a representation of the area under the curve going all the way down to the x-axis. Well, what happens then when we have this other curve? We've got this other one that's going to kind of effectively remove some of that area. So what we're going to do this time in between a and b is we're going to look at that function, and we're going to find the area under that g of x function down to the x-axis between a and b. And we're looking for the difference between those two things. So this one would be the integral from a to b of g of x dx. And really what we're looking for is we're looking for the difference, something like that. I think there's an extra e in there someplace, but we're looking for the difference between those two things. So if I want to find the area between two curves, generally speaking, what we're going to find is when we look at this first one, if everything is defined in terms of x's, what we're going to do is we're going to try to put in this thing that we're going to call this little representative rectangle right here. And you're going to see me use that a lot as we go through this chapter. That rectangle is going in, and it's going to signify, if it's perpendicular to the x-axis, we're going to use everything in terms of x's. If it's perpendicular to the y-axis, we're going to do everything in the problem in terms of y's. So if we're using x's in general, what we're going to do here is we're going to integrate going from, in this case, our a to our b again, the top function minus the bottom function with respect to x. So if we're using x's, it's going to be top minus bottom. If we're working with y's, then this time we're going to be working from y equals c to y equals d. Integral, this time we're using y's, and we're going to start at y equals c and go to y equals d. This time it's going to be the right function minus the left function. The furthest one from the axis over to the one closest to the axis. Again, always starting in that first quadrant. So the right function minus the left function with respect to y. So there's your general setup for what we have going on here. And so let's try what happens when we do this. So set up a definite integral to find the area of this shaded region. We've got two functions. We've got this f of x, which is the curve. So here's f of x, okay, our curve. And g of x is equal to 0. So here's g of x. It's basically, for lack of a better term, it's the x-axis, which is nice. We like it when we have that problem. And what we have here is we have region 1 and we have region 2. Now, with this region 1 and this region 2, what a lot of people are going to do is they're going to want to look at this and go, oh, if I could just figure out what the bounds are, I'd be golden because I could just go ahead and I can integrate this thing. Well, how do I find my bounds? Well, my bounds I find, if I don't have a calculator to do my intersection command, then I'm going to set f of x equal to g of x, and I'm going to solve. So 3x cubed minus 3x, and set that thing equal to 0 and solve, and let's factor out a 3x, and there's an x squared minus 1. So I've got three bounds, x equals 0 and x equals plus or minus 1. So I found those. So I have my bounds. So I know I'm going -1 to 0, 0 to 1. What some people are going to do is they're going to get in a hurry, and they're going to try this. They're going to try integrating this thing from -1 to 1 of f of x dx. And if you do that, we have two regions that appear to be exactly the same size. They may not be, but they appear to be. One's above the x-axis, one's below the x-axis. If you put this right straight into your calculator, you're going to get no area. Well, no area doesn't make any sense whatsoever because there clearly is a region that's shaded, and it should have an area. But according to this orange thing that I have, we wouldn't have one. So you got to be careful. That's why we have to define this top function and bottom function thing. So if I look at region number 1, in region number 1, the top function is that f of x. So when I go to set up my integral, I'm going to integrate from -1 to 0, and my top function is going to be f of x, and my bottom function is going to be g of x, and we're going to integrate that thing with respect to x. If I want to find the area of region number 2, the only thing that's going to be different is that my bounds have changed. So I'm still integrating, but this time I'm going from x equals 0 to x equals +1. I'm still subtracting, and I'm still integrating with respect to x, but this time my g of x function is the top function, and my f of x function is the bottom function. And when you go through and you figure out those values, what you'll find out is this first one comes out to be 3/4, and my second one comes out to be 3/4. Again, you could put them in your calculator, you could do them however you want, same things that we've done before. And now if I want the area of the shaded region, it's going to be those two 3/4 added together. 3/2 square units. So a little bit of an exercise there, and be careful of the orange. Work your way through. You're going to have to set up two different integrals if you have two different regions. Moving on to page 2. So on page 2, sketch the region. So now we've reversed it. Now we have an integral, and it says our bounds are supposed to be going from -1 to 1. So we're looking in between those two values. It says that our top function is 4 minus x squared. Well, that's a parabola. Vertex at 0, 4, opens down, hits the x-axis at 2, 0, and -2, 0. So it looks something like that. So that's my top function. My bottom function would be my x, which is y equals x, which is a line that's basically, y-intercept, slope, work that thing out. So there's my bottom function. Now, I am looking for the area of the shaded region in between -1 and 1. That red part is ultimately what I'm looking for. I'm looking for the area between those two curves, isolated between x equals -1 and x equals 1. So the shaded area is what I'm ultimately looking for right here. So there we've reversed it. Now let's use our calculator to figure out the same thing. So use your calculator to find the area between these two things. Now I'm going to use my calculator. I've actually got my Inspire and my 84 ready to be used, so I'm going to jump right straight to them. So on my Inspire, I've already got my f1 of x and my f2 of x punched in, those two functions. So punch them in as your y1 and your y2. If I do it on my Inspire, what I'm looking at is, well, I'm going to need first to figure out what my bounds are. And on my calculator, the nice part about it is I can go and I can find those bounds pretty easily. So let's go find the intersection. And I'm going to find the bounds in order. It looks to me like there's probably 3 of them. And this first one, I'm going to use this hopefully as a safe lower bound. And I'm going to use this as a safe upper bound. And look what it did. It resized my window. And when it resized my window, what it looks like I've got is it looks like I have an intersection point at -3.07 something. Now I only see 2 decimal places. Now I know there's more. So here's what I'm going to recommend to everybody. As soon as you get that intersection point, store it. So make it gray so it's highlighted, and then store that number. And then store it in such a way that it's easy to figure out exactly which one you're talking about. I'm going to store that one as A because it is the one most on the left. And remember, A is stored. It's the whole number. It's not just -3.07. It's all the decimal places that are stored. I have them. I can use them. I'm ready to go. Now I'm going to find the next one. So let's go find B, the second intersection point. So the second intersection point, let's start with a left bound there. Let's start with a right bound there. Again, here's my intersection point. I've found it. And now let's do the same thing. Let's take that x value and let's store it. And since it's the second intersection point, I'm going to call it B, so it's easier for me to keep track. And notice the bold, which means it's now stored. And then last but not least, let's find the third one. So analyze graph intersection point. There's the safe left bound. There's a safe right bound. There's my third dot, my third value. Now let's take this. Let's store that as a logical C. And when every chance you get, when you store that thing as a value, so now I have A, now I have B, now I have C. Now all I have to do is I have to go back to the other part of my scratch pad and integrate. Well, I'm looking at this thing, and this doesn't look like it's going to be too bad. What I'm going to do is I'm going to set this value up so my left region, so it looks like there's two regions that are being intersected here. My left region, the red function, or F2 is the top one. The blue function, or F1, is the bottom one. So let's go to my scratch, the other half of my scratch pad. Let's choose an integral. And now I'm going, my first region goes from A, whoops, let's go. I don't know why it won't let me choose that one, A to B. And if I tab again, now I can punch it in. So I said the red one was the top one. So that's my F2 of X. And my blue one is the top one. So that's my F1 of X. And I'm integrating that thing with respect to X. So if I hit enter, there's the area of the first region. If I want to find the area of the second region, I could do the same thing. So going back and looking at my picture, second region, blue function's the top one, red function's the bottom one. And now we're going to integrate from B to C. So let's grab that integral again. Let's integrate from B to C. And let's see, this time it's going to be F1 of X minus F2 of X, and I'm going to integrate that again with respect to X, and I hit enter, 24.3372. So there's my second one. Now notice both of those are only showing 6 sig figs. So if I wanted to add those together real quick, what I could do is I could go up and I could grab this number, and I could add on that number, and I've got all the decimal places, hit enter. My area between those two curves, 35.645 if I wanted to go to 3 decimal places. So there's a great start. So there you go. So I've got that ready to go. Now people that have TI-84 series calculators, all I want to do is I want to show you real quick about the storing part. So when I go to graph this, there's my region. Again, let's say that I wanted to do the area of the second region right there where I know that Y1 is the top one and Y2 is the bottom one. So I haven't punched in. So let's start by finding my intersection points. So choose 5 for intersect. Now first curve, there's only two to choose from. So now if I want to find my first intersection point, or this, let's call it this one that's closest to the middle right here, I'm just going to hit enter. Now it found me the intersection point. Now the way that you store this is you immediately quit out of here, and your last answer was that B value. So let's use the answer command and store that number as B. So now there's the same B value that we had on our Inspire a second ago. And now go back and find the C value, which is your number 5 for intersect. And let's go back and find the rightmost intersection point. So first curve, second curve, I got it. Now I can either use my cursor and move to the right, or I can pick a nice easy number like, say, 4 that's closest to that intersection point that I'm looking for. So there's my value, 2.680. Quit out of there. Now take that last answer and store that last answer as C. Now if I want to figure this thing out, I can't do it from my graph on my 84. I've got to do it without the graph. I've got to do it on the calculator way. So go into your math menu, and on math, scroll down until you find your function integral. Now, which one was the top function? Well, the top function we decided was that y1 on our graph. So if I want to graph and make sure, my top function is y1, the cube one. My bottom function is the y2. So if I go in there, how do I get the y1 and the y2? Variables. Go over to y variables. Function. Choose y1. Minus. Go find y2. Variables. Over to function for y variables. And then go down and choose y2. I'm integrating with respect to x, and my bounds are starting at b and going to c. Hit enter. There's the 24.3372 number, and if I had gone through and found the other one on my 84, I'd add it on, and I'd end up with the same value. So long story short, this is all about storing things in your calculator, making them work, and hopefully we've got both calculators ready to go, and we're feeling pretty good about that. So area between curves on with and without your calculator.